Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, everyone. Thanks a lot for coming on this sunny Seattle morning today. So I'm Madan Musawati from the Research and Software Engineering Group, and it's my pleasure to introduce Angelina Lee today. She comes here from MIT. She just finished her PhD, and she'll be joining as a postdoc in the same group starting August, right? Yeah. And so her interests are broadly in all aspects of parallel programming, programming models, programming languages, runtime systems, and she likes working across the stack, both on the theoretical foundations and on engineering problems. So, Angelina.
Thank you. Wow, that's a really nice introduction. Thanks. Okay, so let me just ask, who is in the field of parallel programming? Wow. Okay, so almost everybody. Well, I have some background material just to give you the context of my research, but given that pretty much everyone is in the field of parallel computing, I'm just going to fly through the first few slides. Okay, today I'm going to talk about memory abstraction for parallel programming. But before I get into that, let's say we are in the era of multi-core, right? I think there's no doubt about that. So these are just like a list of top selected, top rated personal laptop that I picked from the newegg.com. And what you notice that was a few $100s, you can get a personal laptop with multi-core. And I think that's pretty striking because right now, basically, multi-core is a commodity hardware. And so how do we get to this point? Well, let's look at the revolution of processors. Moore's law, which says that the number of transistors on chip doubles every 2 years, is still going strong ever since '75. However, at some point, the clock frequency sort of plateaued. And really, the power is the root fundamental cause of all these, because we have reached to a point where we have reached the power density that the device can handle. We just can't cool these devices, and therefore we can no longer keep on increasing the clock frequency. So as a result, the chip vendor, instead of increasing the clock frequency and double the frequency every 2 years, instead now you get double the core every 2 years. So as a result, what that means is that now we have to write parallel program in order to unlock the computation power provided by the modern hardware. But unfortunately, writing parallel program is not as easy as writing serial code, and I'm sure you can all sympathize with that. And I believe to help writing parallel program easier, a concurrency platform can help. And what a concurrency platform is, it's a software abstraction layer that runs between the user application and the underlying operating system that provides a linguistic interface for the user to specify the parallelism of their application. And the software abstraction layer basically handles load balancing and task scheduling for the user code. Okay. And many researchers are interested in the problem of making parallel programming easier. And as a result, there are a lot of concurrency platforms being developed. Also include the TPL from Microsoft and PPL from Microsoft. And this is just a list that I put together since '93, but before that, there's also a lot of other parallel programming language that I didn't include. These are just, I guess, the modern concurrency platform. Okay, so why does concurrency platform help? Because it provides a parallelism abstraction. The job of task scheduling and load balancing are abstracted away and handled automatically for the user application. And which brings us to the topic today, memory abstraction. So I believe properly designed memory abstraction can help ease the task of parallel programming. So what do I mean by memory abstraction? Well, a memory abstraction is an abstraction layer that runs between the user program and the underlying memory, such that it provides different view of the memory depending on the execution context in which the memory is accessed. So just to make it a little more concrete, for example, transactional memory is, I consider, as a memory abstraction because memory accesses dynamically enclosed by an atomic block appear to occur atomically. Okay. So in this talk, my thesis is Properly designed memory abstractions help ease the task of parallel programming. And I'm going to demonstrate that point by showing you two case studies. The first one is cactus stack memory abstraction, which is a cactus stack that interoperates with linear stack. And the second one is memory map reducer hyperobject. It's a linguistic mechanism for avoiding determinacy rays in the multithreaded computation. Okay. Any questions so far? Okay. So this is the outline of my talk today. I will mainly focus on the cactus stack memory abstraction, and then I'll briefly touch on the memory map reducer hyperobject and draw a concluding remark. Okay. So for a concurrency platform, I believe there are three desirable criteria that a concurrency platform should provide. The first one is what I call serial parallel reciprocity. And what that means is that the parallel code should be able to seamlessly interoperate with serial code, including legacy binaries. And the second one is it should provide good performance. And what that means is that if the application has ample parallelism, you should see near perfect linear speed up when you run the concurrency platform. And finally, the last one is bounded stack space, which is to say that when you run the computation in parallel, it should consume reasonable amount of space compared to the serial execution. Well, why are these three the desirable criteria? I like to demonstrate the point using a cartoon. We have an engineer, and then we have a customer. Well, the customer would like to parallelize the software, and the engineer says, sure, use my concurrency platform. Well, if today the engineer can only satisfy 2 out of the 3 criteria, then what he needs to say is, well, you need to say he decided to forego the SP reciprocity, which is say interoperability between parallel code and serial code, then you need to ask the customer to recompile all his code base. Well, but that may not work so well because the customer actually used third-party binary. You can't recompile source because he doesn't have the source. So if that's not an option, maybe the next one to forego is the space usage. And so what the engineer might say, well, upgrade your RAM because I don't know how much space you're going to consume. I don't think that will go too well. So the last one to forego, if that's also not an option, is basically performance. But, well, if you can't get the performance writing parallel program, then you might as well just write the serial code. So I believe these are the 3 desirable criteria, and we really want to operate in the space where we get all 3 criteria. Okay, but it turns out that there seems to be a fundamental trade-off between the 3 criteria. Our group and the practitioner in the field actually thought about different strategies to build concurrency platform that can satisfy all 3 criteria, but it turns out that many of the strategies that we can think of satisfy only 2 out of the 3 criteria, except for the last strategy, which is what I'm going to focus on today. And so the cactus stack problem is basically the problem of how to satisfy all 3 criteria simultaneously. Okay, so now we know what the cactus stack problem is. Let's see why we have this problem. Well, so if you think about it, in serial code, people typically use a linear stack. And the execution of a serial language can be thought of a serial walk of the invocation tree. So here on the left, I'm showing you an invocation tree where A calls B and calls C, C calls D and E. These are the view of the stack when the function is active. So when B is active, it sees A and B on its stack. When D is active, it sees A, C, D. And the linear stack works really well for the serial program. When you call the function, you allocate the stack frame. When it returns, it pops it off. And so essentially, if you think about it, this is very space efficient because B and C occupy the same place in the stack. And the parent and child are allocated in the contiguous memory address space. So that's the linear stack. And furthermore, it follows the rule pointer where the parent can pass a pointer to its children, but not the other way around. Okay, so that's the linear stack. So what's a cactus stack? A cactus stack is essentially just like a linear stack. It follows the same rule for pointers, except for now it needs to support all the views for stack for all the functions that can be active in parallel. So in this case, I'm showing you the same invocation tree, except for I'm using red arrow to indicate that these functions are spawned. I haven't defined spawn yet. But basically what it says is that B and C and its subcomputation can potentially execute concurrently in parallel. And what that means is that the linear stack no longer work because B and C now can be active at the same time, but they cannot occupy the same space. So linear stack is no longer sufficient. Okay, right, so that is cactus stack. Now, obviously, people have been building parallel languages for many decades. So what do? Well, in many parallel language, when they use a cactus stack, they basically build a heap-based cactus stack. What that means is that when a function becomes active, you allocate the frame in the heap. So the parent and the child are not allocated in the contiguous space, but rather you have a pointer from child pointing back to the parent so you know where to return to. And this including Cilk-5 and Cilk++. And with this strategy, good time-bound and space-bound can be obtained, but it failed to interoperate with legacy serial code because now you have to follow this heap linkage where the call return is performed via the frame allocated in the heap. And when you have a piece of legacy serial code, it does not understand the heap-based cactus stack. It still allocates things on the stack. And so therefore, you fail to interoperate. And so as I said, many strategies I would try to think of failed, except for the last strategy. And I'm not going to get into all the different strategy, but one thing I'm going to say is the main constraint of all these strategies is that once a frame is allocated, the frame's location in virtual memory cannot change. And that's a problem. Okay, so that is the cactus stack problem. And next, I'm going to overview Cilk-M, which is a system that we built to basically solve the cactus stack problem. Okay, so first of all, throughout this, the rest of the talk, I'm going to use the programming model in Cilk. Here, I have a very naive way of calculating Fibonacci code where you just do fib n-1, fib n-2, and then you sum the result together. And obviously, fib n-1 and fib n-2 can compute in parallel. So to write this naive fib computation in Cilk, the way you do it is basically you spawn fib n-1. And what spawn state is that the named child function may execute in parallel with the continuation of its parent. So in this case, the continuation is the call to fib n-2. So in this case, fib n-1 can may execute in parallel with the call to fib n-2. Sync, on the other hand, is the counterpart of spawn. It serves as a local barrier, which states that the control cannot pass beyond point until all previously spawned children in this lexical scope have returned. And note that these Cilk keyword grant permission for parallel execution. They do not command parallel execution. What that means is that the programmer specified the logical parallelism of his application uses these keywords, and the underlying runtime system will schedule them accordingly. And whether the fib n-1 and fib n-2, the true parallelism gets realized or not during actual execution depends on the underlying resource you have. And the runtime scheduler will schedule accordingly. Okay. Any questions so far? Okay, so what's Cilk-M? Well, Cilk-M is basically a work-stealing runtime system based on Cilk that solves the cactus stack problem using thread local memory mapping. So what's thread local memory mapping, or TLMM? TLMM is a virtual address range in which each thread can map the physical memory independently. So what that means is that in this range, all the threads sees the same virtual addresses, but they can potentially map different physical pages in that region. And so the high-level idea is that at the system startup, this is the stack where you have heap, stack, and data. And the runtime system will allocate the heap and the data and the code in a shared region, but allocate the stack in the TLMM region where each thread can map independently. And at very high level, this is what the solution looked like. And right now, bear with me with an unreasonable simplification. Let's assume that we can map with arbitrary granularity. I'll come back to this point later. So we have 3 workers. We have, again, the same invocation tree. And say P1 is now actively executing on B, and P2 is actively executing on D, and P3 actively executing on E. What you can do in the TLMM region is that now you can allow the thread to share a frame by mapping the same physical page for that frame in the same virtual address. And in this case, say for example, if P1 and P2 share the stack prefix of A, they can map the physical memory for A at the same virtual address and map the actual same physical page. On the other hand, they don't share B, C, and D, so they would map different physical memory after frame A. And with that, because A is allocated at the same virtual address for both threads, if A pass a reference down to its descendant, for both worker, they will see the same virtual address, and when they dereference that virtual address, it will actually point to the same physical memory. Okay. Any questions so far? Okay, I think I'm just gonna, yeah. That's a good question. I'll get to that, although much later. So, if.
Sorry.
Yeah. If I don't answer your question by the end of the talk.
Just a question, so I know I understand it. So suppose in P1 I take a stack address of a local variable in B, and I secretly pass it along to P2. They will really map to different, it will go all wrong, right? It will not.
That's correct.
That's right.
Yes.
And I understand it then. Right.
Yes. Yep. Okay. Although I have to say, in multi-threaded programming, you shouldn't do that because that's bad
sure.
practice.
That's what I was saying. It's just that I really understand it. It's not a critique because
Yes.
I totally agree. You should not take stack addresses
Okay.
in the first place.
Yes. So yeah, your understanding is correct. Okay. Right. So this is the high-level idea, and with TLM-based cactus stack, we guarantee time-bound and space-bound. But before I get into the time-bound and space-bound of a TLM-based cactus stack, I have to first go over the time-bound and space-bound of heap-based cactus stack. So in Cilk, using a heap-based cactus stack, say we call TP as the execution time on P processor. Then T1 basically equates the execution time on single processor, which means that's the total work of your computation. On the other hand, T infinity, you can think of that as the execution time if you have infinitely many processors. And so what that translates to is the span, or some people call critical path, of the computation, which is the longest dependency chain in your computation. So we define parallelism to be T1 over T infinity. On the other hand, with stack space, we call SP as the stack space consumed by P processor, and S1 as the stack space consumed when you execute serially on one workers. And with that, using a heap-based cactus stack, Cilk guaranteed the following time-bound and space-bound. First, the time-bound is TP equal to T1 over P plus big O T infinity. And what that bound tells you is that when the number of processors you execute is much smaller than the parallelism you have, or i.e. your application has ample parallelism, then the first term dominate, and therefore when you execute on P processor, you should see near perfect linear speed up. On the other hand, it guarantees space-bound that states that each worker does not use more space than S1. But with heap-based cactus stack, it does not support SP reciprocity. Now, with Cilk-M, using TLM-based cactus stack, to define the time-bound space-bound, I have to use an additional parameter called Cilk depth. Cilk depth is the maximum number of Cilk function nested on the stack during a serial execution. So here, when I say Cilk function, I mean a function that can contain spawn and sync, meaning that the function itself contains parallelism. So note that the Cilk depth is not the same as spawn depth. For example, here I'm showing you an invocation tree where I'm marking the parallel function, the Cilk function, in blue, and I'm marking the regular ordinary serial function in green. And the red arrow indicates spawn, and the black arrow indicates call. In this case, the Cilk depth is 3, because you have at most 3 Cilk functions nested on the stack, i.e. A, C, D. On the other hand, spawn depth is only 2, where C spawns D, D spawns F. So Cilk depth is defined as the maximum number of Cilk functions nested on the stack during serial execution. Okay, so this is the Cilk-M guarantee. Now, in terms of time bound, instead of big O T infinity, we have this term S1 plus T in front of the T infinity. And so what that means is that with this bound, your application need to have a little bit more parallelism in order to get near perfect linear speed up, which is this. On the other hand, for the space bound, we have an additional plus d term. And right, so one thing I forgot to mention, here we are always measuring the stack space in terms of number of pages. So in this case, we have an additional plus d term. But by giving up just a little on the time bound and space bound, what you get back is serial parallel reciprocity, which means that the compiler no longer need to distinguish function types at the call side. And whether you have parallelism or not is dictated only by how a function is invoked. So you can actually spawn both a Cilk function or a C function, or you can call a Cilk function or a C function. And this was not possible in Cilk 5, or in Cilk with heap-based cactus stack. Okay, so we implemented this. We basically implemented a Cilk-M prototype based on the open source Cilk 5 runtime, which Cilk 5 was the one with heap-based cactus stack. And TLMM, well, traditional operating system does not provide such functionality as TLMM, so we also modify open source Linux kernel to provide support for TLMM. It's not a big modification, about 600 lines of code. And we ported the runtime system to work with Intel's Cilk Plus compiler. What that means is that we can actually compile a piece of C or C++ code that contains spawn and sync, and it will run on our runtime system. Okay. So let's take a look at the performance. And as I said earlier, the Cilk-M has the time bound of this, where the C is S1 plus D, and we compare that with Cilk Plus. So Cilk Plus is also a Cilk-based runtime system developed by Intel, and the runtime system has time bound that's like the heap-based cactus stack. And so when you look at the performance, here what I'm showing you is I have a list of application, and I run each application 10 times and take the average with standard deviation less than few percent. And I take the Cilk-M running time and normalize that by the Cilk Plus running time. So what that means is that if it's below 1, that means Cilk-M runs faster, and if it's above 1, that means Cilk Plus runs faster. And you can see that the performance of the two are actually comparable. In terms of space consumption, and now this is the time-bound S1 plus D. So again, we use the same set of benchmark, and we have the first column D, which is the Cilk depth that I just defined, and S1. This is the stack space used during serial execution measured in number of pages, and this is what the bound predict. But the bound is actually kind of pessimistic. And in practice, when you run in parallel, these are the actual SP over P, the number of pages on average used per worker when you run on P workers. And as you can see, the amount of pages used per worker is within 2 times factor compared to the serial execution across benchmark, even though the space bound predict that you will use much more. And later, as I describe how each of the components work, you will see why the bound is kind of pessimistic. But yeah. Okay. Any questions so far?
Do you have comparison of the space consumption between Cilk-M and the base Cilk Plus?
No, unfortunately, I do not have that comparison, but that's a good question. It's at the time when we did this work, there was actually the runtime source for Cilk Plus was not available, so we couldn't it wasn't open source, but now it's actually open source. But at the time it wasn't, so we weren't able to take it and try to instrument that. Okay. Oh, but to answer your question, we do actually have a space-bound comparison number with Cilk 5, which uses a heap-based cactus stack, which has a better time bound. And the space usage that we have is comparable. I don't remember the number off the top of my head, but I can show you later after the talk. Okay, so Right, so that's the Cilk-M overview. And now I'm going to go into a little bit more detail on each of the components, on how things work. So the first one is the Cilk-M work stealing scheduler. Okay, so in the work stealing scheduler, during execution, each worker maintains a work deck of frames. It basically keeps track of what function the worker has responsible to execute. And for the most of the time, the worker manipulates the bottom of the deck just like a linear stack. So for example, if a worker executes a call, it pushes the call frame onto the bottom of the deck. On the other hand, if it executes spawn, it pushes the spawn frame onto the bottom of its deck. And here I'm marking the frame using how the frame is invoked. And obviously, all the worker can do that in parallel. On the other hand, if a worker does a return, it pops the frame off the bottom of its deck. So as you can see, for the most part, the worker's behavior operating on the deck just like a linear stack. However, the worker's behavior diverges when a worker runs out of work to do. So in this case, the green worker has run out of work to do, so it randomly chose a victim and steal from the top of the victim stack. So in this case, say the green workers happen to choose the blue workers to steal, and steal from the top of the deck. Okay, so can anyone tell me why the green workers steal 2 frames instead of 1 in this case? I'm checking if you're actually paying attention. In this case, yes, you're right that when successful steal occurs, that's when true parallelism is realized. Yes?
The continuation of the spawn is a candidate for parallel execution. The continuation of the call must be executed sequentially.
That's correct. Yay, someone's paying attention. Okay, yeah, so, well, I'm not saying the rest of you are not. I'm just, okay. No, that's what I'm saying. Okay, yes, you're right. In this case, because the second frame is called, and what that means is that the parent cannot be resumed until this function returns. And therefore, when the green worker steals, it has to steal both frames together. Okay, right. And so now the green worker successfully steal, and it can continue to execution. And as you pointed out, this is the point when the true parallelism is realized. Okay, and the theorem from Bloom-Bloom finalization states that with sufficient parallelism, workers steal infrequently, and you get near perfect linear speedup. Okay, so that's the gist of work stealing scheduler. The next, let's look at TLM-based cactus stack, see how we maintain a cactus stack on top of this work stealing runtime system. So again, bear with me still, we are using the unreasonable simplification. And I have the same invocation tree, A spawn B and C, C spawn D and E. And here I'm showing you 3 workers. And I'm showing you the TLM region of each of the worker. So during execution, the worker basically used the stack like a linear stack. And so P1 execute A and subsequently spawn B. P2 comes in and decides to steal, and it happened to steal A because pretty much that's the only thing available to steal right now. And when P2 steal A, it map, i.e. not copy, the stolen prefix. In this case, the stolen prefix is just frame A to the same virtual addresses. So it mapped the physical memory correspond to frame A, aligning the same virtual address as what it is in P1 space in its own TLM region. And then it continue execution. And at this point, it just operates on it like a linear stack. P3 comes again and steals C. Probably speaking, it should be stealing A, fail to make progress, steal again. But let's just, for the sake of simplification, let's say it steals C. So it steals C from P2. In this case, the stolen prefix corresponds to A and C. So it mapped the physical memory correspond to frame A and C in its own TLM region, aligning at the same virtual address as in P2 space, and then resume and continue execution. Okay, so again, just to emphasize, because they're mapping the same physical memory and aligning mapping at the same virtual address, when you have a pointer of local variable, it will realize the same virtual address on all workers, and when you dereference it, it will point to the right physical memory. So now, obviously, one cannot map at arbitrary granularity, so let's see how we address this. No, oops, yeah, okay. So here, again, I'm showing you 3 workers, and I'm showing you the Cilk-M region. And let's say I'm using horizontal line to denote a page size boundary. So again, P1 execute and B. And in this case, when P2 comes in and steal, it mapped the page corresponding to frame A into its own Cilk-M region. And since a worker can only map at the page granularity, inevitably, it's going to map part of the frame B. And so it needs to be careful not to clobber frame B that's executing on P1. So to do that, before P2 resume, basically it advances stack pointer to the next page boundary, which creates some fragmentation. And then it continues execution. Similarly, for P3, if it steals C, again, it mapped the pages where A and C reside on into its own Cilk-M region. And again, inevitably, it's going to map part of B and D. So again, before it resumes execution, it needs to advance the stack pointer to the next page boundary, which further create additional fragmentation. So in Cilk-M, we use a space reclaiming heuristic where we reset the stack pointer back to where it was once the function sync. Because once a function successfully sync, you know there's no longer any parallel subcomputation, so you know you can reclaim the space. Okay, so that's how the runtime system maintains Cilk-M-based cactus stack. And let's look at the analysis, how we maintain the bound. Okay, so again, let's review the heap-based cactus stack, where it basically states that let S1 be the stack space required by our serial execution, and SP be the space required by parallel execution. Using a heap-based cactus stack, each worker does not use more than S1 amount of space. And the gist of the proof is basically saying that the works-linear runtime system maintains what we call busy leaf property, which is say that every active frame, and when I say active, it's basically a frame that's has been invoked and has been allocated. Every active leaf frame has a worker executing on it. And so what that means is that you can at most have P active paths from the root of the computation to leaf, and there is one worker on every leaf. And from the root to the leaf, you use at most S1 amount of space. So the entire computation, each worker uses at most S1 amount of space. With the Cilk-M space bound, it's very similar except for you have this plus P plus D term. And this is because we do also maintain the busy leaf property, but because every time when we have a successful steal, you have to advance the stack pointer to the next page boundary. So in the worst case scenario, if every Cilk function that realized the Cilk depth D term gets stolen successfully, then you have that many number of fragmentation in your stack. And so therefore, you have this additional plus D term. But back to the number, as I said, in practice, it's actually using much, much less space because the bound is kind of pessimistic. For one, when you have successful steal, you are mapping the same physical page. So the bound is actually double counting those pages. And furthermore, the worst case scenario described by that derived the bound rarely happen in practice, because when you have ample parallelism, most of the time the steal corresponds to near the root of the computation, and then each worker just execute. Okay. In terms of performance bound, on the other hand, using a heap-based cactus stack, this is term. And it's just a stat. At every time step, the worker either do work or steal. And after constant round of steal, you will successfully steal and make progress on your critical paths. And so in this bound, the constant hidden behind the big O roughly correspond to the overhead that you have for performing a successful steal. And using a heap-based cactus stack, that overhead is just switching a few pointers. But in the Cilk-M, using Cilk-M-based cactus stack, because every time when you advance, when you have a successful steal, you have to advance the stack pointer, and you have to do the page mapping. And in the worst case, you have to map S1 plus D number of pages. And that's why now the C term is no longer a constant, but rather a function growing with S1 plus D. But as I said, the worst case scenario rarely happens in practice. And what the corollary says is that now you need to have a bit more parallelism, meaning you have this additional term here in order to get near perfect linear speed up. Okay, any questions so far?
Why is it rarely happening in practice? If you steal at a random place, it will be in the middle of a page.
So
Then you have to advance half a page.
So recall that in a work stealing algorithm, we always steal from the top of the deck from the victim. And what that means is that you're always stealing the oldest frame executing. And when your application has ample parallelism, what that means is that if you imagine your computation tree, you're stealing near the root of computation tree, and then each worker just do work for the rest of the time. Because whenever you steal a big chunk of work.
It's near the beginning of the stack and so of a page.
Yes. And it maintains, yeah, well, we can talk more after, yes. Right. Okay, so that's the analysis of Cilk-M. And now I'm going to tell you more about how we maintain support for TLMM. So when we start this work, there are two possibilities. We can either make a worker a process. What that means is that every worker has its own page table, and by default, nothing is shared, because in an operating system, traditional operating system, when you have a process, each process has its own address space. And what that means is that you don't have to make changes to the operating system, but since these concurrency platforms typically execute applications that assume to run on shared memory, now you have to use mmap. The runtime system has to manually do mmap to allow you to share the rest of like the heap and the data and the code. And that's not so ideal, because when user application does something to call mmap, the runtime system actually have to intercept that mmap call and do the same, synchronize it across all the page table of all the worker and do the same mapping in every page table. And this actually happens more common than you may think, because in, say, library implementation of glibc, when you allocate memory that's larger than like 128 bytes, it may do it under mmap underneath that the user code is not even aware of. So we took the second approach, which is to say we just make the worker as a thread, which is the original abstraction. And what that means is that worker shares a single page table, and they share the entire virtual address space. By default, everything's shared. And what we need to do is basically we need to reserve a region to be mapped independently. But using this strategy, user call to mmap can operate correctly. Okay, so how do we do that? Yep.
Sorry, why? Just explain a little bit more why we need to change the operating system.
Well, because traditionally, when you have multiple threads within one process, they share one single page table, and the entire address space is shared. So you cannot have this abstraction where each thread sees the same virtual address range but map different page.
You're on a platform above there. You're developing this platform above there, aren't you?
Yes, but the mapping of what physical page map at what virtual address is handled by the operating system.
The thread switch has to change.
Right, like the way that thread sees its virtual address space. That's handled by the operating system. Okay, so how do we support that? Well, ideally, this is what we like to do. Ideally, what we like to do is take a region that's mapped independently, and that space, we can call it the TLMM region, and the rest is just shared. So we will have two separate page tables for each thread, where one page table manages the independent region and the other manage the shared region. So when you access an address, if it falls under TLMM, the thread will access its own like private page table. If it's fall under the shared region, it will access the shared page table. But that doesn't quite work, because in some hardware, the hardware walks the page table, and each thread must have a single root page directory. So you can't have this two separate page table. And so what we did instead is we allocate a unique root page directory for each thread, and we reserve one entry to be mapped independently. And however, if some thread accesses some address in the shared space that causes the shared region to be initialized and mapped to some other page, then we synchronize the root page directory across all threads to point to the same thing. And so what that means is that you must synchronize the root page directory. But that does not occur often because one entry in the root page directory corresponds to a huge space, and the only time you only need to perform synchronization, at most one synchronization per root page directory entry when it's first initialized. So the synchronization does not occur often. And once it's initialized, it just accesses it. Any question? Yeah.
So you were just, in the previous slide, you said, oh, you know, processes don't work because you can't do mmap, and threads don't work because we have just one page table. So what do you do here? Because now you're saying, oh, I can have multiple page tables per thread.
Right.
So you're assuming processes here, or you assume?
Okay. So each thread can only have one root page directory. So what we did is that we have, so in the page,
If each thread is really an OS thread,
right, if each thread is an OS thread,
and there's only one root page.
there's only one page table, which means there's only one root page directory. And when I say root page directory, is this, so this is like one page table, right? That's the root page directory.
One for thread 0 and one for
Right,
thread 1.
so to enable TLM abstraction, we basically, each thread still have single root page directory, but they are different root page directory across the threads.
That is same as having different page tables for a single process, right? So in the sense, if there's a context switch between one thread to another thread in the same process, you would have to change the page table.
That's correct. You will have to flush your TLV in. Yes.
So how do you do that? Like how do you, like I'm wondering, what did you actually implement? Is this running only on Linux, or can I run this on Windows, or does it run on your modified OS?
So we did modify the OS. This is only implemented on Linux. I think you can do the same thing on Windows.
Now I get it. So you did modified OS. So
Oh,
you can
yes.
do the multiple threads in one process.
Yes.
Okay, now I get it. I thought maybe
Okay.
you actually had some trick. I was hoping, like after this slide, you would say like, oh, but we have a trick, so you can actually do it anyway for.
I see. Okay.
you
yeah.
know,
Sorry. No tricks. Sorry to
But
disappoint.
no, but that's a big. So actually, it is a big drawback, right?
To modify the operating system.
Yes.
Some may argue that, but yes, customer might. But I do.
I think you can kind of say like, oh, the drawback, it's okay because I get like amazing speed ups, right?
Well, so for one, it allow you to satisfy all three criteria simultaneously. And furthermore, I think it's actually a very interesting abstraction that the operating system can provide. Because traditionally, you know, you either have thread share everything, or you have processes that nothing is shared. Well, why can't we have something between where you have partially shared and partially private? And I will demonstrate in my second study, we actually also use this abstraction from the operating system to implement a different linguistic abstraction. And other people have studied different linguistic abstraction that this seems to be a really useful abstraction for the operating system to provide.
So I would think that this, I mean, there would be other applications of, you know, having different page protection domains within a single process.
Yes.
And are you aware of prior work of, like, you know, up in the systems community, people trying to do this for different things?
So I am aware of different applications where this would be useful, but they all did it by basically creating worker as processes and then do the manual map. But right, like if you have to do that to implement some abstraction, then this would be really useful. Then you don't have to do this whole manual sharing and yeah. Okay. So right, so this is TLM-based cactus stack, but there's one limitation where basically we do not work for codes where require one thread to see another thread stack, which is, I forgot his, sorry, what's your name?
Den.
Den, right? Den's earlier point, like, well, if you pass a local reference to local variable on a stack from one thread to the other thread, it doesn't work, right? Okay, so in summary, Cilk-M is a C-based concurrency platform. It satisfies all three criteria simultaneously, and we basically, to allow that, we basically use a TLMM-based cactus stack memory abstraction, and we also, on top of that, we use legacy compatible linkage to allow the interoperability between parallel code and serial code. Okay, so that's the cactus stack memory abstraction. Next, I'm going to just briefly touch on the memory map reducer hyperobject because I think I'm running out of time. Okay, so reducer hyperobject. What's a reducer hyperobject? It's a useful linguistic mechanism for avoiding determinacy race in a dynamic multithreaded region. So what do I mean by that? Well, let's see a piece of code. Say you have a piece of code. You do some computation and store the result of computation into an array of strings. And then later you want to concatenate the string together in the same order from index 0 to n. And if you want to parallelize this code, naively, if you just parallelize it, say, let me just run all the iteration in parallel, there's a determinacy race because now logically parallel subcomputation can access the same variable and at least one of which is array. And in this case, every single access is array. So it's a determinacy race. And as a result, the output string is non-deterministic. You no longer have this guarantee of the concatenation is from index 0 to n. Okay, and so reducer is basically a linguistic mechanism to avoid exactly that. To use reducer, you basically declare res, the final output string, as a reducer instead of just a regular string, and now you no longer have determinacy race. And furthermore, the output of the reducer is deterministic. It's the same output as the sequential execution, provided that the operator that you use is associative. Okay, so conceptually, how does it work? Well, during parallel execution, here I have 3 workers, and say the loop iteration is divided across 3 workers. Essentially, conceptually, what the reducer does is that it creates a local view for each worker to accumulate its update on. And at the appropriate point, these local view gets reduced or combined together in a way that produces the same result as serial execution. So the result is determinate, provided that the operator is associative. And in this case, it is string concatenation is associative. And note that it just needs to be associative. It doesn't have to be commutative. Okay. And so, in short, the reducer allows different logical branches of the parallel execution to maintain coordinated local views on some non-local variable. Okay. So with memory map reducer, the high-level idea is that given that the premise of reducer is to have local views for some non-local variable, and you coordinate the access between them and combine them at the appropriate moment, wouldn't it be cool if you can leverage the virtual address translation provided by the underlying hardware to provide this mapping the reducer to different local view for different worker? And so that's what we did. And comparing to the existing approach, using a memory map approach, we get faster reducer access time. Every time you access the reducer, it needs to be mapped to some local view. And this access is now much faster. It has parallel overhead. What that means is that the application can potentially scale better. And finally, it's simpler runtime implementation, actually, which is always good news for me. Okay, so that's what we did. And here I'm showing you, so we implement this in Cilk-M. And this is showing you the overhead normalized to L1 cache. So using memory map reducer, each access essentially translates to 2 memory access and a predictable branch. So when you measure that against, when you normalize that against 1 memory access to L1 cache, it's about 3 times overhead. On the other hand, when you use the existing approach, it's actually about 12 times overhead. And just to show you, as a point of comparison, if you use a spin lock to protect the access variable, it's over 12 times overhead. Okay. And to implement this, there are actually 4 questions that we need to address. One, what operating system support that's required to do the memory map reducer? How do you support reducer with different type sizes and lifespan? And how do you support a data structure that we need to use for reducer that allow you to do constant time lookup and efficient sequencing? And finally, how can you allow efficient access from one worker's global view by another worker? And I'm not going to go into detail of these 4 questions. And the only thing I'm going to focus on is what operating system support. And it turns out that Cilk-M is actually very good for that. And obviously, the idea is that allocate local view for a given reducer for each worker in the Cilk-M region at the same virtual address. And so now in Cilk-M, in the Cilk-M, besides the stack, we also allocate a region for reducer for that purpose. Right. OK, so that's the gist of memory map reducer. I'll be happy to talk about it if you have questions on that. OK, so concluding remark. So recently, researchers have started exploring ways to enable memory abstractions using page mapping or page protection mechanism, right? So like you asked earlier, these are all examples of that. So C# with atomic section, I believe it's work coming out of Microsoft UK. And example like Grace dthread, they basically use the page protection mechanism to enable deterministic execution. There's also some work on using page mapping protection to detect race and avoid deadlock. And obviously adding to the list is the Cilk-based cactus stack in Cilk-M and memory map reducers. So this is the end of my talk. And if you're going to take away one thing from this talk, is this. I hope I convinced you that if you have properly designed memory abstraction, you can ease the task of parallel programming, either directly by mitigating the complexity of synchronization, such as in the example of reducer hyperobject, or indirectly by allowing concurrency platform to utilize resources better, such as in the case of Cilk-based cactus stack and memory map reducer. And finally, the second takeaway. It seems like the Cilk-M mechanism may provide a general way for building memory abstractions for multi-threaded programs. OK, thank you.
So we have time for a couple of questions.
So in the beginning, you motivated that this part is related to the fact that you have to recompile existing code in order to use it as the normal case. Can you explain a bit why you have to do that? I mean, it seems like maybe you could just use the existing code and it grows its own stack normally on top of the intermediate layer, right?
Sure, yes. So I guess what you can do is, the main problem, so without recompiling code, you need to enable some way to switch between heap-based cactus stack and linear stack. But that's not really the main problem per se. You can use a wrapper to enable that. But the problem is that then you might run into a space-bound issue where each worker actually used more than S1 amount of space. And I can go into an example if you like, but I'm wondering if I should take more questions or I should spend. OK, and we can chat afterwards.
Yes.
Yeah.
One more question. Yeah. So you said in the reducer, which I like, by the way, that you don't need commutativity. I'm a little bit surprised because it means
Right.
You have to
Yes.
make sure that all indexes that you go over are like
Yes.
somehow sequentially handed out.
In the runtime system, basically, so notice that in the work stealing scheduler, the execution is always, so we do steal the continuation of parent instead of stealing child. And so what that means is that let me back up a step. So for Cilk, if you remove all the parent, a Cilk program actually has a serial semantic in the sense that when you remove all the Cilk keyword, that's a valid C function. And when you execute the Cilk program on a single worker, the execution order is the same as serial execution. And the way runtime stealing scheduler work is that whenever you steal, between each steal, the code that's executing on a worker is actually the same as the serial execution order that you would have. And what that means is that you just need to keep track of the different relationship between your parent and child whenever you perform a successful steal, which we already maintain in the runtime system. And so when you combine, you know exactly what are the relationship between the two local views you have. And you just combine accordingly. And so, does that answer your question?
No, maybe you
Sorry,
take it
maybe I didn't
offline.
quite understand.
So, yeah, maybe we'll take it offline.
Okay, yeah, sorry, maybe I didn't quite
I'll
understand.
meet you later, so that'll be good.
Okay.
Yeah, I guess to follow up on his, let's say there was this loop of 100 things that was covered by this reducer object, and then now you want to steal. Do you partition it by 50%, or how would you know what to partition it by?
Right, so the way that the parallel loop implemented in Cilk is that essentially you do divide and conquer on the loop space. So the first worker will execute the first half, and when you steal, you actually steal the second half. Right. So it's like, it's actually a binary tree divide and conquer of the loop iteration space.
Any more questions? So actually, Angelina has some open slots in her schedule today. So if you'd like to meet with her, send me an email, madanm@microsoft.com. So let's thank the speaker.
Thank you.